All right, it's Eli. I'm back again. We're going to show off like demo modes 3 and 4 with the example FRDM-TFC board. So if you remember last time, demo mode 1 was this demo of the, how to use the servos. Demo mode 2 is pretty similar, but instead of doing the servos, we're doing the motor. So I have a macro. This actually sets a line high. If you look at the schematic, there's an enable signal. We enable the H bridges, but I have a function called set motor PWM, and its arguments are kind of like the servo. You give it a number between 0 and 1. I'm sorry, -1 and 1. Where -1 is all the way backwards and +1 is all the way forwards. And if you wire yours up and it goes backwards, it means it has your motor leads are backwards. So just like the servo, I just dumped the read pot return value because it's already scaled to -1 to 1. So we should be able to make each wheel move with each pot. And notice I don't gate this to a ticker. I update it as fast as it'll go, which is fine. And then, but in here, the ticker, it kind of works like in the servo, but the LEDs will go the other way. So let me get my webcam again here. All right, sorry, it looks a little, I got this free program and to view my webcam, and it has some goofiness on the screen, but that's okay. So I was still in servo mode here, so I can still move those around. So I'm going to get them back to neutral so we don't take off. So what I'm going to do now, sorry, there's no real good way to focus this camera. I'm going to put in demo mode 2, and so it might get a little shaky here. Flip switch 2 off. All right, and you notice this wheel turned because I had my pot turned a little bit. So I'm going to turn this pot. There we go. I don't know if you can hear that in the video. Now I'm going to go the other way. I'll slow it down. Oop. Don't want my computer to go to sleep. Now my other wheel I can get moving. Because in this car there's 2 independent motors, we can kind of control each one. So that's kind of cool. There it goes the other way. We'll just make it go slow. So the idea here, what's kind of cool is we could actually make an active differential. And I'll do a lecture on that later on, kind of how you make that work. But when you go around a turn, remember your outside wheel always has to go faster than your inside wheel. So if you advance that a little bit, you can help you steer. And that's important because servos are very, very slow. It turns out you can do most of your steering with the rear wheel. So you definitely want to take advantage of that. So other than that, that's how you use this API. You can dig into the functions to see how they work. In my TFC init, I set up some TPM channels. You can see what I do there. And by default, I set it to 5 kilohertz switching frequency. You can play with that if you want to. I'll let you look through the code because that's part of the learning experience. But you have kind of a working reference. Now, lastly, we have this 5-pin header for the line scan camera. So I have mine hooked up. Make sure on this cable, I had a cable that was not keyed in any way. Make sure you don't plug the cable in backwards because you will blow up the camera. Take a look at the schematics and make sure on the bottom side, because there wasn't room on the top of this circuit board, you can see signal names. Make sure they all match up because you will put power in a very bad place if you hook it in wrong. So what I'm going to do first is put this into demo mode 4 while I'm sitting here. And all right, so I'm in demo mode 4. Now I'm going to go to the code and talk about code for a minute. All right, demo mode 4, I call it like Freescale garage mode for the lack of a better term. And basically what it does, it's going to beam data, it's going to send data from the line scan camera to LabVIEW. So we're going to take this in a couple steps. First, you notice my ticker, I'm going to send it about 10 times a second. And then I also have to synchronize it to when there's actually data ready. So the implementation I have in this code is probably a little bit more advanced. Now, if you just want to use the code, you really don't have to understand anything about how it works. But if you read the data sheet and the timing diagrams, I implement it in a way where it's all done in the interrupt ADC interrupt routine, and I use the programmable interval timer and the ADC to do all the stuff in the background, so I don't have to do anything in the foreground. So what I'm going to do is first show you how you can use it at a high level, then we'll go from there, and I'll show you the application. So one other thing that's interesting here is that, let me open up my control panel. Just give me 1 second here. Control panel, in my device manager. Is whenever you plug in the TFC, or the Freedom board, you should get this Open SDA serial port. It's a virtual COM port created by the SDA interface, and it shows up on some UART pins on the Freedom board. So we use that. I can use this virtual COM port to send data. And I'm going to have a LabVIEW program I'll show you in a minute. I have another video where I'm going to talk about the terminal, but at this point, if you call this macro terminal printf, this will actually just go over that serial port. The default baud rate, if I go in TFC config, is 115200. It is a fully queued interface, meaning you put data in a queue, and then I have other functions that will move the queue in the background, because you don't want to sit and wait for things to flush out a serial port because it's kind of slow. So that's what I mean by fully queued. You know, you don't write directly a serial port. You write to a queue, then it gets flushed out automatically. So terminal printf, it just simply writes to the terminal, which is a serial port, which in my case was COM7, and we'll look at that in a bit. So here's how you use it. In the background, there is a variable called line scan image ready. When the next frame is ready, this gets set to 1. So if you just kind of wait for it to get set, you simply clear it, you know a new line scan image is ready. Then I'll kind of zoom in here. There are two 128-byte arrays called line scan image 0 and line scan image 1, because there's two interfaces. Those are simply a byte array of the actual data. All the ADCs in this code works at 8-bit, where 0 is black, 255 is maximum saturation. Now, in the background, you won't see this. This is actually double buffered. So whenever as soon as you trip off this variable, line scan image ready, the buffer you get with this array is actually the the buffer that just got recorded. There's actually a secondary buffer. It's a set of ping pong buffers that the new data is coming into. So you're good for a little while with this buffer. You might want to do a mem copy and copy it out as soon, but that's up to you. But it is double buffered. So all I do here is I have like a battery level indicator. I kind of move lights around so I see stuff that's going out. What I do is, for me to decode it, I simply write a carriage return /r/n. I write a capital L colon, that indicates the start of my line scan data. Then what I do, this terminal printf uses all the same arguments that printf does. I write hex values, 8-bit hex values that are comma separated. First I write 128 of them for line scan camera 0. Then I write the second 128, which is line scan camera 1. So to a terminal, you'll get L, 128 values from the first camera and 128 values from the second camera. Then it's all finished with, when it's all done, a carriage turn line feed. So you can pick that up. So I'm going to show you a couple things here. So this will just loop and loop and loop and go for it. So let me open up my favorite program called Putty, and I should be able to go to COM7, and we should see this data fly by. 115,200. All right, look at that. There it is. It's just the raw data coming from the camera. So that goes really fast. We can't see it. I'm going to close the serial port. Yes. Now, I wrote a LabVIEW program that is included with the source distribution. If you go to R, your release R0 or whatever, it's under LabVIEW, Garage Line Scan. So I actually opened this up. So if you're a student or professor, you can get LabVIEW for $20 from Studica. It's very cost effective. So for $20 you get LabVIEW, and it's a good program to have. So this is LabVIEW 2011. They may have a newer version. But basically, here's the way this works. First, you pick your COM port. This should find it if it exists. Now, sometimes if you unplug the USB port while things are powered up or it's connected, it gets all funky. If that happens and the COM port doesn't show up, you'll have to look in your device manager. Sometimes the best thing to do is unplug everything, power everything down, close LabVIEW completely, even the splash screen, and open it back up. So I just knew I was COM7, and I'm going to press go. So if I did everything right, there it is. Now, let me move in the data here. I have two channels of data, and it looks a little screwy now, but I'm going to fix that in just a second. There's channel 0 and channel 1. Well, channel 1 isn't populated on the board, so I'm going to hide it. So here's channel 2. Now, as I kind of move closer, now I got line data because I'm kind of far away from it, and there's a lot of light in this room. What I'm going to do here is, while you're watching the screen, I'm going to get a screwdriver and adjust my... Oh, I messed up. And here's a good example. Everything just kind of reset because I hit a cord, so I'm going to close that. Yeah, lost connection. That's fine. LabVIEW, just give me a second. I got to completely close out. Now let's see if it comes back up. Just give me a second. No, it did not. I just got to try to reset it here. Sorry, just give me 1 minute here. Try this one more time. Okay, I'm back. Oh, because I didn't fill in the COM port, it's unhappy. You got to fill in the COM port before you start. This isn't really an advanced LabVIEW program, so you can upgrade it if you wish. So what I'm going to do here is, I have the camera on a mount, and I'll show you this with my webcam. Alright, where is my webcam? So let me get the webcam. I'll kind of show you the physical configuration here. So I have this camera on this mount, which you can actually find on Shapeways. And I have this piece of white paper with a line. Alright, and there I'm looking at it. So what I'm going to do is, you notice I'm going to move the paper left and right, and you can see the data moving back and forth. Now you might ask, like, okay, it's sensing that black line, but it's not dipping down very low. So what that means is this camera is very, very saturated, and there's a lot of light coming in. So I'm going to do like one trick here. Let me see if I can find something to jam. All right. Put behind my camera. I got to find it. Where is it at? Sorry. All right, as simple as sticking, I have my checkbook here, behind the camera. Notice how it got a lot better. So light pollution is a big deal. But you can see the peak moves from side to side. And back in the code, I'll show you some other parameters to play with. But there it is. You can play with the camera. You can tear apart that LabVIEW program to kind of see what it's all about. The other thing I can do is adjust the focus. Notice I just adjusted that focus and brought it in quite a bit. And that line got a lot sharper. All right, but the focus also, you're going to find there's certain aberrations that happen at the edges. Pixels 0 to 10. As you play around with the focus, you'll see oddball things happening over there as well. So I'm going to take my checkbook out. Oh, look at that! Look at all that light pollution. So let me put all that away for a second. So that LabVIEW program's there. Like I said, LabVIEW's $20. Put on your own student machine, or if you're an instructor, it's $20. So that's kind of nice. You just need an EDU address. Now let me show you a couple. We're going to dig into the plumbing here. Now this is a fairly advanced example of how to set up the line scan camera. Most of the routines I've seen are done in a main loop with bit banging. That's okay, but I really wanted to control things like exposure time. I did it all in interrupt routines, so my main loop, wasn't encumbered by dealing with that. So I'm going to go in linescancamera.c, and you'll be able to see a little bit of the plumbing. There's actually two files, a couple files you have to use. There's this init linescan camera. There's nothing in here you really need to modify. You can kind of see how my buffering system works. There is a function called set line scan exposure time. So as it turns out, while I'm talking here, I'm going to try to bring up the data sheet. House line scan camera. All right, it was the House 1401. I'm going to bring up the data sheet here. This product page. Sorry, this is all going on. I should move this over here. Taos is now AMS. Okay. Linear sensor array. And yeah, this is it. 1401CL. Let's download it. So basically, this sensor array is just a big shift register. There is a photo receiver, an integrator to integrate charge developed, and then a big shift register. But the output of the shift register, it's analog. You have a clock and this start signal. So you can read down through this. But basically, the way it works is to get the process started, you bring SI high and low, and then you do the clock it a bunch of times. There is 129 clock cycles, 128 generate data. Then on every edge of the clock cycle, you get data. So you see at the rising edge gets you data, and then you want to sample. But here's the trick: is that the time from the 18th clock cycle to the rising edge of SI, that time is the integration time. The integration time in each pixel. So the longer the integration time, the more light it lets in. So controlling that's actually pretty critical. You want to know how much integration time you want, depending on lighting, but also you need this at a fairly constant rate, meaning SI, bam, bam. There are some preferred rates. We'll talk about algorithms in another video, usually synchronized to like your servos. But you want to be able to control it. And depending on how light or dark, if the track's really dark, you need more integration time. If it's really bright, you need less. So by default, I think mine is like 25 milliseconds, maybe 50 milliseconds. You have to look in the code. But you can kind of control that. Now I'm going to step through really quick how this code works. So if we go in the ADC.C, it turns out everything, including the potentiometers, is done in the interrupt routines in the background. The ADC code I took from the sample code on their website. But here's what I'm gonna show you. In the init routine, I init the ADCs for 8-bit mode, and then I have a state machine. To let the ADC interrupt routine know what's going on. The next thing I do is I have the programmable interval timer interrupt me at the rate I want to get frames out, which is related to the integration time. So I enable interrupts. So let's just start here. Whenever I get, let's say it's every 20 milliseconds, I set up the programmable interval timer to interrupt. Whenever it interrupts, what I do is I clear the mask and then I set SI high. All right, and so that's right here. That's every time the pit interrupts. Then what I do is I set the ADC state. The first thing I do is I capture some potentiometers. And everything kind of happens in this routine. So, and then I literally set up the AD converter. I tell it, that's the channel I want. I'm going to tell it which side of the mux and to enable interrupts. So then as soon as the AD converter is done, I come to the interrupt handler and I look at my current state. If I captured pot 1, I dump the value in my pot array, then I configure it to pot 1. And then when that's done, notice I have the state set here. The next time I jump into the interrupt handler when it's done, I'll come to this case block. Then I grab the battery. But you notice here, in each state, here I set Taos clock high. I'm going to do a little delay. This isn't good coding practice, but it works. To twiddle the clock. All right. Then after the battery channel's done, I move into the capture line scan. And in that state is where I loop through each pixel. Now it's important to know I don't sit in here and loop. I just have my state machine set up that on every conversion I kind of keep track of which pixel I'm at, where my working buffer is, and whatnot. So then when it's all done, I don't do anything. On my last, pixel, I actually don't restart the analog digital converter. He'll just sit in this init state. So what starts it? Well, the pit. The pit's going to fire again at this integration time rate. Or it's closely rated. It's not exactly, but it's close. So when it's all said and done, I don't have to do anything in my foreground loop except for look for this flag, all right, and then I have 2 pointers that I can use in my main loop that give me the most recent image. So I'll let you study that code kind of on your own. It may take you a little while because it's using 2 different interrupts. It's a little more advanced. But at the end of the day, notice all I have to do is when I get this line scan image ready, do something with it. You may in your end application want to synchronize it to something like servos or whatnot. I actually do have in the servo function, or in the servo, using the overflow from the primary counter used in the timer channel. I actually have a servo ticker that gives me an up count whenever the servo whenever a new servo cycle starts. You may want to use that. I don't know. So there we go. There's demos 3 and 4. In between all of those, you have enough code to kind of get this board working. You may want to add to it. Feel free to email me, emh203@gmail. There may still be a bug or 2 in here. Or if you want commit privileges, and you can help maintain this code. So that'll be all for today. Thanks for your time.